Okay, so let's start our second lecture. So in this lecture, we will prove the Rouch theorem. So before I state the theorem, let me just first introduce some terminology. Okay. So that gamma, uh, let's use this gamma. Okay, be a simple closed curve. So some notation. Okay. So simple means it doesn't have any self-intersection. Closed means that it's like a closed loop that there's no breakups. Okay. So the start point is the same thing as the end point. That's the closed curve. And that the open bracket be is interior. So we know by the Jordan curve theorem, for any simple closed curve, we have a interior. So basically, the idea is that it breaks the whole plane into two pieces. Like it separates the whole plane into two pieces. One piece is bounded, one piece is not. So the bounded one we define to be the interior, and also yeah, and and we let the bracket gamma be uh, okay, we define gamma to be the interior union to curve. Okay. So it basically is like the interior and the boundary. Okay. So this is like that. Okay. Okay. So let's start. Let's state the theorem. So. So okay, so maybe this is better. Okay. All right. So okay. So we state the theorem. So suppose. The big bracket gamma. So and then so be careful that this is not open, right? So the thing is that what we do is that we say that it is analytic on a bigger set that contains like bigger open set bigger bigger open set that contains gamma. Sorry, contains this set. And then so the modulus of FZ is bigger than the modulus of GLD for Z. Yeah. So basically on the on the boundary, F, the modulus of F is bigger than the modulus of Z. And then the function fg plus gz and the function fz have the same number of roots inside curve gamma. Okay. Yeah. So basically these two functions, they have the same number of roots inside the curve gamma. Okay. So what we do is that so when we talk about the number of roots, basically we can think of a theorem called the argument principle. Basically, it's saying that it gives you a way to calculate the number of roots of homomorphic functions. Okay, so yeah, okay. So okay, so here is the proof. That this nt to be 1 over 2 pi I line row over gamma. So basically the idea is that we introduce a function like an intermediate function, like so here so the idea is that we introduce a new function, let's say so we introduce a new function like fz plus t gz. Yeah. So basically a family of functions, and then and we are interested in, so namely for the argument principle, this only work for one function, right? So we are saying that the root of the function, this number is the root of a single function inside the curve whatever the curve gamma it is. But in this case, if we introduce a family of functions, then this is not only a number of root of a function anymore. For any t, you put in, it gives you the number of roots for that function. For that function corresponds to the t. Okay. So actually, we introduce a family of functions, g prime z, and for this family of functions, so basically, so what we do is, so we use the argument principle for any of them. Yeah. So which the number of roots depends on t. Yeah. So the idea is that if we show that this nt is so this nt we know before that it can only be like integers, right? So if we show that this nt is continuous, right? You know, like a continuous function, basically it cannot jump, right? So basically, if we show that this nt is continuous, then we just get a result. It must be a constant. Okay. Okay. So yeah. So what's the idea? Okay. So what we want is that we want to show that this nt is continuous. Okay. So yeah. So before we it's like so t is between 0 and 1, right? So of course this when t equals to 0, right? So as long as we show that nt is continuous, then that means this family of functions, let's say, let's see, ht of g. Yeah. So we know that this family of functions basically have the same amount of roots, right? So if this nt is continuous. So therefore, when does the family start? When t equals to 0, it starts this function f, right? And then when t equals to 1, this is just z. It's just f plus gz. So therefore, we are just done. So the only thing that remains to show is that, so let's say our goal is to show that this nt is continuous. Okay, so just keep that in mind. Okay, but yeah, so sorry, but before we move on, like what really matters is that this nt is well defined, right? So because we need to show that the denominator never reaches 0. Okay, so in order for this to be defined, right? Yeah, so because for the argument principle, you need the function to have no root on the curve, right? Okay, so why this new function, or this family of new function doesn't have any roots on this gamma? Well, if it does, right? So if this, let's say, this yeah, so can it have 0? So namely, if it has, so if let's say it's equal to 0 for some z in gamma, right? So if it does, then we have fz is equal to negative t gz, right? However, the thing is that you see that so in our assumption, this f, the modulus of f is always bigger than the modulus of g of z, right? So basically, in this case, so this implies that the modulus of fz. So yeah, so remember that this t is always between 0 and 1, right? So t between 0 and 1 means that this so this, the modulus of this guy, which is just tgz is actually less than g, right? Because this t is between 0 and 1. So it must be less than equal to modulus of g of z, right? so which is a contradiction because this FC is bigger than G. The modulus of the FC is bigger than modulus of G. Okay, so which is a contradiction. So I will use this as a contradiction. Okay, so therefore we know that we cannot have them equal to each other, right? Okay, yeah, so this all set. All right, so we show that the yeah, okay, so now we show that this function is continuous. Okay, so remember that continuous means that so we will use some okay, so we'll use yeah, so yeah, actually I think we will show something stronger. Yeah, we will see something stronger. So the thing is that okay, maybe let me just start it. Okay, so okay, so yeah, so the idea is that we will show that this will pick any 2 points, right? Because this NT basically is a function being defined on the interval 0, 1, right? So basically the idea is that we pick 2 points, T1, T2 from 0, 1, and then we will show that this the idea is that we show that this n of so yeah, so basically the idea is that so pick this T1, T2 in this closed interval 0, 1, and then we want to show that this n of T1 minus n of T2. Remember this one is like the difference, right? Like remember like this help like a difference of output, and then this one is less than equal to like some constant times T1 minus T2, right? So let's see, yeah, so if we show that, then we have like the alpha and delta, right? So if like T1, yeah, so for, okay, yeah, so for any epsilon bigger than 0, right? So we know that, yeah, so there exists a delta to be like whatever epsilon over C, right? And then this less than delta implies this less than epsilon. Yeah, okay. Yeah, actually this is like a Lipschitz continuous, right? Yeah, okay. All right, so how do we show that? Okay. Okay, so that T1, T2 is interval 0, 1. We have is n of T1 minus n of T2, which is equal to, so basically so basically we were just doing T1 minus the okay, so this is like we first compute the difference. Okay, so okay, so let's just make the common denominator. Okay, so 1 over 2 pi I. Let's see. Yeah, we do the cross multiplication. So yeah, so this will be a mess. So here we have. So let's do that. So I wear like jeans, which is pretty good. Okay. Okay. So let's see. So here we will first multiply. Okay. So I'll just give you a few steps. Okay. So I'll just multiply out f1 z fz, and then yeah. So plus T2 f1 z g of z plus T1 g prime z f z plus T1 T2 g prime z gz, and then minus so this times that gives you fz f prime z minus let's see, T2 f z g prime z minus T1 g prime z f prime z minus wait, did I mess up somewhere? Let's see, let's finish this. T1 T2 g prime z squared. Wait. Yeah, so sorry. Yeah, I made a mistake here. Yeah, so this should be GZ. Okay. So yeah, sorry. Let's see. Yeah, this has no problem here. Yeah, so this is F. And then it should be GZ here. And then it should be GZ times G prime Z. All right, beautiful. Okay. All right. So let's see. We have some term to cancel out, right? So let's see which term. Wait, there is no term to cancel out. Yeah. Okay. So here this is one term, right? And then yeah. So there's T1, T and T2. Okay. So what's that? It's just like this T1, T2 stuff, right? So namely, so equal to. So bottom one, I won't bother copy it up. And then for the top one, so here, this coefficient is in terms of T2, and then this one is also in T2, so we can combine these two. So let's see, so we get this T2 times F prime Z minus F Z G prime Z. And then plus, let's say T1. So T1 G prime D F Z. Minus GZ F prime Z. All right, so you see that the integrand, the integrand should be, so the integrand you see like f prime z gz, right? And then f prime z gz. So the integrand is like some reversed, right? So this is like f z g prime z and that, right? So yeah, we can further simplify this. So how about just making it, we use the T1, right? So, so let's put a negative sign here, and then we put a plus here, okay? So here, F Z G prime Z, and then minus GZ F prime Z, okay? So they're the same, right? So let's see, let's say, let's pull out this, T1 minus T2, right? So we can get something like this one, like that, times this G prime Z F Z minus GZ F prime of Z GZ. All right. Okay. So now we so now what we want is that we want to analyze this stuff, right? So because we want to find like a uniform bound for these for the things other than, because we know that this gamma is like a simple closed curve, right? So if we can show that, so if we can show that the integrand is bounded, then we just get our goal, okay? So how do we show that this is bounded, right? So so namely we want an upper bound for the numerator and the lower bound for the denominator. Then we get a bound for this one, okay? So why there is an upper bound and why there is a lower bound? Okay, maybe as you know, like because this gamma is like a compact set, right? So a compact set basically it contains this minimum and maximum. Yeah. So basically, we can pick like a lower bound. So these are all continuous for fixed T1, T2. These are all continuous. Okay. All right. So maybe I'll write this one. I just copy it down. Okay. Yeah. So for context as the image is compact. So therefore, okay. I'll see. Okay, never mind. So let's see. Okay, so therefore. So if you have a compact set, then we take the. Okay. All right. So let n to be the soup of Oh, hi, see you again. Okay.
I'm gonna work clean.
Oh, sure.
You're not gonna write here.
No.
Okay.
Okay. Thank you. I'll finish soon. Yeah.
Take your time.
Okay. Yeah. So let m to be the soup, and then okay, and then this small m to be the int of this Okay. So then we have that when we take the modulus. So this is less than okay, so let's add one. So let this L to be the length of this curve, right? So we have L to be the length. Okay. So then this is less than equal to 1/2 pi times this L of modulus of T1 minus T2 times m over n. Okay. Wait, I missed something? Oh, sorry, I think I missed something. So, yeah, so actually this is So this is not that because yeah. So this is actually the theorem over z modulus of fz minus modulus of g of g. Yeah. So why is that true? Okay. Yeah. So I know this is like I do it again. So this. Okay. So why this is true? So okay. So you have modulus of fz plus t1 g of z. So do we have do we want something smaller, right? We want something smaller. So okay. Yeah. So yeah. Okay, we know there is something called the inverse triangle inequality, right? So so basically the idea is that if you have like two vectors, so the magnitude of a plus b, if you have this vector as the a, and then if you want to say that what's the smallest thing you can get when you have two vectors? Well, the smallest things you can get is that they are in the I think the thing that they are kind of in the opposite direction, right? So yeah, so that's how I interpret the inverse triangle inequality, but I'm not sure whether it's correct or not. So leave any comment below. Okay, so yeah, so I think this can also be proved, right? So yeah, so if you have I don't remember, like a plus b minus b, right? It's less than equal to a plus yeah, I think this is a so yeah, a plus b plus negative b, right? Okay. Yeah. So by the inverse triangle inequality, we get f z minus modulus of t1 g of z, right? So we know that the modulus of we know that this guy is less than or equal to that guy. Okay, so this guy is like actually bigger. So yeah, we want minus okay. Right, okay. So, okay, we're getting it. So this one is actually bounded below by this one, alright? Okay, so therefore, this is why if we take the in of this one, this is a lower bound for the denominator, which provides the upper bound. Okay. So actually, because this T1, T2 is arbitrary, right? So it's actually bigger than equal to this small m squared. All right. Yeah. So therefore, we know that. And then. So, yeah. So if it is not constant, then by the intermediate value theorem, this is there has to be something inside stuff which values. Okay. To be honest, I'm a bit not sure, but yeah. So yeah. Okay. So. Right, so if NT is continuous, yeah, so intermediate value theorem implies that okay, yeah. All right. Yeah, so this is the lecture.